Next technique for dealing with multiple dimensions is called a scatter plot matrix. So it is a matrix, and inside each element of the matrix is a scatter plot. As you can see here, I have on the y dimensions, I have abrasion loss. It starts from 32 and goes to 37 or 372. And on the x dimension, I have hardness. And again, they kind of starts at 45, goes to 49. Seems to be a little bit of an inverse correlation. So the harder it is, apparently, I guess it makes sense that the abrasion loss is less. If the, whatever hardness, if it's harder. So that's one. The reason it's a matrix is because it looks like a matrix. And I have here another one, and that looks at abrasion loss versus tensile strength. So you can just follow this diagonal, the second diagonal, to see what the data is, and kind of you can even use the first diagonal for it. I've seen variations like that, and then look at different correlation between two different attributes. One interesting thing here is that if it's a full matrix, then this panel is a flip over of this panel, where the x and y axes are inverted. So here the abrasion loss was the y-axis, here the abrasion loss is on the x-axis. But other than that, it is the same representation. So many times what people do is they don't display the lower part, and that kind of keeps it a little bit smaller. Yet still, here I have 3 dimensions. If I add a fourth one, how big is my matrix going to be? 4 by 4, so it's going to be 16 of these cells. If I take 4, the diagonal out, then it's going to be 12, and so I can get rid of one of these 6 more. There's still quite a lot of them. So here I can kind of do away with 3. If I add 4 dimensions, they go to 6. If I add 5 dimensions, I go to 25, get rid of 5. It goes to 10 and so forth. So it's an not exponential, but it's a quadratic increase. 6 dimensions, I need about 36 of these for a full matrix. So it tends to grow a lot more than anything else. That may be the one thing to consider. The other thing, individual scatter plot works like a scatter plot, but they only put together 2 data dimensions, correlation between 2 only. You can see how they're grouped together, if there's any clusters related to one dimensions or the other. You can see if there's correlation, inverse correlation, or just completely random. So it does provide a lot of information, but it tends to get bigger. So if I have 10 data dimensions, now I'm going to end up with something like 50 of these, a little bit more than 50. It's 100 if I do a full matrix, but if I only keep half of it, it's roughly around 50. So it's not, with the other one, with the Attribute Explorer and the linked histograms, I need 10 panels for 10 dimensions, so it's a lot smaller. It just doesn't grow as fast. Here's another one with 4. Kind of see what happens when I have 4 dimensions. Like I said, I only need this part, but still that makes it all the way to 6 panels. You can, like I said, see the distribution. So here there aren't that many student-faculty ratio in that area. Here you can see clusters a little bit. So that's one cluster. This is the second cluster. It helps to show some of these. It's not always visible, but you can look at that. One problem as dimensions grow, and we kind of remember what if there are some dimensions that behave kind of the same way, like highway miles per gallon versus city miles per gallon? They tend to kind of go together. So what if I have 20 of these dimensions and 4 of them go together one way and they kind of tend to behave the same? And then I have 3 more that tend to behave the same. How do I see that? And the problem here, in order to determine that, I would have to find a good order. Otherwise, these graphs will tend to look a lot kind of random. They tend to look random in here. There's really no order between them. So what happens? What if I move this graduation rate from here to here and I swap them? Would I see some sort of an overall pattern in the matrix? So the order in which I place my dimensions can make a difference. And there's a couple of papers I've seen in trying to solve that more or less automatically. And I think they refer to themselves to that idea as skagnostics. So here is data from a Greenland station. I don't know how many of these dimensions are, but it's 1, 2, 3, 4, 5, 6, 7. Looks like about 20 or so, 19 dimensions. And however, they order them in a way that you can see patterns emerging. So there's groups. This one looks completely different than all the other ones. So that dimension tends to be different than the others, but you can see that there's groups. They look the same. If you look at neighboring, like the things I circled, the scatter plot looks about the same. If I start moving dimensions around, I'll start lose that sameness. Then everything will look kind of scrambled. Imagine that I can take these dimensions and move them around, take this row and column and kind of swap it with this one. And if I keep doing that, eventually I won't be able to see any pattern. But right now the pattern is apparent. So how do they try and do something like that? Again, order matters. And here is what they use. They use this idea of classification. And I guess the best thing is to focus on this graph. So here they look at, I can't read it. I'm just going to bring my glasses. Outlying, are there outliers? In this representation here on the left side, there are no outliers. On the representation on the right, they have a lot of outliers. So you can kind of see how you can classify them based on outlying. Skewedness. And kind of see you have a lot of grouping here. Here they're all kind of close together. Not a lot of, they call that skewedness. Clumpy. You have clusters that are clumped together, and as opposed to here that I have one big continuous thing. So not a lot of clusters. Big continuous area that kind of goes everywhere, all over the scatter plot. Here is whether it's dense or sparse. So here is sparse, here is dense. Again, everything to the right tends to satisfy whatever name they gave it. Striated. So here, not a lot of striations. These are some W formats, but these, you kind of see lines going down. So they call those striations, and they came up with algorithms to measure that for each of them. Convex. So obviously this is not convex because I draw a line pretty much every 2 points. The definition of a convex, if you draw a line between 2 points, you're still inside the same area. So this is very convex because any line kind of fits inside. A circle is convex. Letter V is not, because everything you draw, or a lot of points are outside. Skinny, whether it's skinny or fat, I guess you can kind of see where this is really fat. This one is a little bit fat, and this is really skinny. Stringy, does it look like a string or more like a blob? And finally, monotonic, does it always increase or decrease? So these are some of these categories they can try and put these scatter plots. So they first generate all the scatter plots, and they try to kind of categorize them. And after that, they tend to cluster, they reorder the dimensions, so they kind of go together. Again, the same view here. You can see that things in the middle, they tend to be kind of fat. Things, green ones tend to be different. Red ones tend to be maybe more monotonic. So that's how they try and group them. Obviously, there's no perfect one, because if you move one dimension around, you can take one graph and move it too far away from the others. You're not moving a single graph, you're moving a whole line and a whole column at a time, every time that happens. So that's one way. Again, keep in mind, I have to order the dimensions on this one in order to get something that makes sense to group them. And therefore, I can see that these dimensions tend to behave one way, these dimensions tend to behave another. And they're close to each other, they're separated from the other ones. So instead of looking at individual points, I kind of look at overall pattern of what's happening. Another thing, and this is not only true, but I have it here. It's not for the matrix, but for the individual scatter plot. The scales that we use for the axis may matter, and that's true of many things. So every time I have an axis, try to figure out what's the best scale. So here is, this is the same data set represented in multiple ways. Here is the kind of original, everything is linear scale. Here they only show half the scale. This is square. So it tends to move faster that way. It stretches it a little bit. This is square root, tends to push the dimension that way. This is log. You start to see clusters if you use a log scale here. They separate into 3 clusters. They use the inverse function, so 1 over x, so if this is x. Or they probably do it for y, 1 over y, because that's what you normally play with. And you start to see 2 clusters. Again, this is log, different kind of log. And this is a sigmoid function. And you start to see separation in there. Again, keep that in mind, that scale may matter. Not all programs are going to give you all these scales, but as you can see, there's quite a big different view on a normal scale versus a log scale.